Okay, let's start. Now, we have a Y monotone polygon, and our goal is to triangulate it. And I'm going to describe another plane sweep algorithm, which uses a stack. So we don't, in this plane sweep algorithm, we don't have the status structure. Our status structure is actually a stack, okay? And we don't maintain a list of edges that intersect the sweep line. We don't need to do that. We don't need to have a binary search tree because since it's a Y monotone polygon, we know that our sweep line always is going to intersect in two edges, okay? Since it's a Y monotone polygon, that's one of the main properties of Y monotonicity. If we have a sweep line which is horizontal, this sweep line intersects this Y vertical line. The intersection is at one contiguous region of the polygon. We cannot have two contiguous regions, so that's the definition of monotonicity. So we don't need to have, we don't need to store edges intersecting the sweep line. And here in our study structure will be a stack. We are going to maintain a stack. And it's not actually very related, so it's going to be like this. Let me now describe it. Here, any Y monotone polygon, again, forget about the degenerate cases in which we may have horizontal moves, for example, horizontal edges. Let's assume that we don't have any horizontal edges. All the edges are like this. So this is a Y monotone polygon. Okay. Still, the Y monotone polygons, they are not convex still, so it's not very trivial to see how we can triangulate this. A solution may not be easily apparent, but what we are going to use is something like that. Again, we are going to, the left chain is an ordered list of vertices in Y coordinate, and right chain also. So given a Y monotone polygon, by determining if there are no horizontal edges, again, these can be dealt with later without simple modifications to the algorithm, but just assume that we don't have any horizontal edges. If we don't have any horizontal edges, it means that there is a unique top and unique bottom vertex of this Y monotone polygon. Okay, so that's one result of this assumption. If you don't have any horizontal edges in a Y monotone polygon, then you have a unique bottom and unique top vertex. And these top and bottom vertices actually divide your polygon into two separate chains, the left chain and the right chain. Now, the left and right chains, they are sorted in Y coordinates. So what we do is we combine these two chains. Okay, like the merge step of the merge sort algorithm, this can be done in linear time. By going over these two lists, we get ourselves a single list of Y coordinates in decreasing order. And we are going to maintain a stack, and on our stack, and we are going to process these vertices one by one with a sweep line, okay? We are going to sweep them, downward sweep. And when we come to a new vertex, we are going to compare this vertex with the ones on the stack. And our stack invariant is going to be this. At any time, during the processing of this vertex, of this new vertex, we are going to be drawing diagonals to the vertices that are on the stack. And whenever we draw a diagonal, it means that we have a triangle and we split this triangle out of the Y monotone polygon. So the polygon is going to be decreasing, and when we draw a diagonal here, the top part are always going to be, we're always going to have triangles at the top part. So we have dealt with the top part, we can move downwards. So when we draw diagonals, we generate triangles, and these triangles split off they're processed. We don't need to deal with this part anymore. So that's the main invariant, and the the vertices on the stack are going to describe, at any intermediate stage of the algorithm, is describe a shape like this. So I don't know the end point of this edge. So there's one edge on left-hand side or right-hand side, and there are vertices and I don't know how this edge goes either. So these will be the vertices on my stack, and the top part of the triangle, the Y monotone polygon that I haven't processed, is always going to look like that. Meaning that I'm going to have, it's going to be composed of two chains again, and one chain I have a long edge, which is, I don't know its endpoint yet, it's unprocessed long edge, and the other part is going to be a series of vertices whose interior angles are greater than 180 degrees. Okay, only this may be less than 180 degree, but since I don't know this vertex, it may also be, I mean, it may, the other edge, actually the other edge is going to be low. This is, only the last one can be less than 180, but here these edges are going to be greater than 180. So this is the invariant that I'm going to observe. I don't guarantee it right now, but when I'm processing the new vertex, you are going to see that this property is always going to be maintained. Okay, so here is, sometimes it may be also like this. If I have only two vertices at the top, if I have only two vertices at the top, it may look something like that as well. Again, this is the same image. So the top of the unprocessed part is going to look like a funnel upside down, and this one also looks like a funnel upside down. So here's how I'm going to process a new vertex. When this new vertex that I take in my that I encounter during plane sweep, if it is an endpoint of this edge, I will easily draw diagonals to all the vertices on the stack, and it's going to give me these three new triangles. Okay. And I'm going to push this one on the stack, and the last one here on the stack is going to be pushed back onto the stack. So when I'm done processing these vertices that were previously on the stack, I will be left with unprocessed part like this. Okay, so when there are two cases when you process a new vertex. The first case is when this new vertex is on the opposite side of the vertices that are currently on the stack. If it is it can be either on this edge, or it can be here. The new process one can be here on this edge. Okay, if it is on this edge, again I'm going to draw diagonals to the vertices on the stack, but I will not be able to draw all the diagonals. Okay, I was able to draw this diagonal, but this diagonal is intersecting the polygon edge, so it's not valid. So I will draw diagonals as long as I can draw them. I'm going to pop the vertices from the stack one by one. I'm going to draw this diagonal, and this vertex is going to be taken out of the Y monotone polygon, but I will not be able to draw this diagonal. The reason is that the angle here, again, between these two is going to be is greater than 180. So I'm going to pop this one out. This diagonal, this triangle is drawn, but this one I will not be able to draw it. So this vertex is going to stay there. So and this funnel property is maintained. So the algorithm is this, in short. Each time initially the stack contains the two vertices of the first edge, the incident edges of these, and each time I'm going to process a vertex during plane sweep, I'm going to process the next vertex which has the highest y coordinate. And I'm going to look at this vertex, whether it is on this side of this funnel or on this side of this funnel. If it is on, I'm going to look at the stack vertices, I can also store which side they're on. If they're on an opposite side, if the new process vertex is on the opposite side, I'm going to draw diagonals to all the ones on the stack, except the last one on the stack, because I already have an edge to that. The last one on the stack is going to be the upper end point of this edge, so I don't need to draw this edge again as a diagonal. This edge is already there, so I don't need to draw this one. So I'm going to draw edges to all the vertices. I'll be able to draw diagonals to all the vertices on the stack, and after I do that, I push this one and this one again on the stack. So this is one type of vertex in which the vertex is on the opposite side. If the vertex is on the same side of the vertices that are on the stack, I can know which side it is, because I know, since we have two separate chains, I know their chain labels, which chain they are from. So I have this information initially. I know each vertex, whether it's on the left chain or on the right chain. So when I'm pushing these vertices on the stack, I can have this chain labels with them. So by looking at the top vertex on the stack, I can know which chain it is on. So when I'm processing a new vertex, I can know whether it's on the same chain or on the opposite chain of this vertex on the stack. So if it is on the same chain, if this new process vertex is on the same chain, I pop vertices from stack and I draw a diagonal and see whether this diagonal intersects these edges between the stack vertices. If it doesn't intersect, if it's a valid diagonal, I continue popping vertices as long as it's a valid diagonal. But if it's an invalid diagonal, I stop at that point. I push this one also on the stack, and I continue processing the next vertex. So this one is going to draw n-1 diagonals at most, if I have n vertices in total. And the total, it's going to be a linear time. I'm going to process each vertex only once during this plane sweep. And since there can, these pushing and popping seems like in a loop, but a pop vertex is not pushed again. When I draw a diagonal, I just get rid of this vertex. So I'm going to at most draw at most n-1 diagonals. So in total, the algorithm is going to be linear time. Okay, so let me write the algorithm in detail so you are going to understand the details. So I think this space will be enough. So right now our input is a list of vertices u1 to un sorted in y coordinate, in decreasing y coordinate. So step one, initialize an empty stack. Empty stack S, and push u1 and u2 on the stack. Okay, u1, what is the label of u1? Is it left chain or right chain? Since it's the top vertex, you can label it as both left and right chain. Okay, so based on u2, whether it's on the left or right, u1 is going to be considered left or right chain. Okay, if ut is going to be uniquely a left or right chain vertex. So ut is going to inherit whatever u2's label is. So you can do it like that, because here at any point we are on the stack, we are going to have vertices from the same chain. Now, so initially u1 and u2 are on the stack. Then for j is equal to 3 to n-1. So un is the end vertex. This one, un is the end vertex. until the end vertex, what we do is, if uj and the top of S are on the same chain. Let's do it on different chains first, on different chains. Doesn't matter. On different chains. So if uj and the top of S are on different chains, as I said, we can find this easily. If initially your y-monotone polygon is giving you as two different chains, each vertex is labeled with whether it's left chain or right chain vertex. So we can find this by just looking at the property attribute of this vertex. We can find whether the top of S and uj are on different chains. If they're on different chains, what we do is then pop all vertices from S add diagonals from uj to these vertices, except the last one, and then we push uj minus 1 and uj on S. Okay, so we have also drawn a diagonal from uj to uj minus 1, but at the end, after we drove these diagonals, uj and uj minus 1 are going to be the new top of the unprocessed part. Okay, so everything above uj and uj minus 1 at this point will be processed, will be triangulated, will be drawn diagonals in between and split off from the y-monotone polygon. At this point, our stack is going to have only two vertices on top of it, and it's going to look something like this. So uj minus 1, uj, okay? So we don't know where this one ends, we don't know where this one ends, okay? So it's going to be like this. Now, so uj is at that point on top of stack. So if we come to a new vertex, if this uj plus 1 is on different side from, again, uj, if, for example, uj plus 1 is somewhere here, we are just going to draw a diagonal to this one, and now these two will be on the stack. So if our vertices, in terms of, so this gives a nice property. If your left and right chains are sorted in terms of y-coordinate, and in this y-coordinate sorting, if you have an alternating vertex, left, right, left, right, left, right, you'll be able to easily draw diagonals between consecutive vertices to triangulate this polygon. Okay? The problem becomes when in these y-coordinates there are many vertices on one chain, and there are some vertices on the other. You will not be able to draw diagonals in between every pair of vertices. So it will, triangulating a y-monotone polygon will be very easy. You don't need even an algorithm if this sorted list of vertices, I mean this one, right, left, right, left, right, left, right, left. Here we have right, if the, yeah, this left, right, and so we'll be able to triangulate this easily by drawing diagonals between these right, left vertices easily. So if they're on the same chain, so else, this is what we do. We pop one vertex from S, and pop other vertices. So in a while loop, this is what you do here. While the drawn diagonal is inside polygon P, continue popping vertices and draw diagonals. Pop vertices and draw diagonals. If it is not inside P, we push the last vertex back, and we also push uj on stack on S. Okay, so that's it. And after this while loop, what we do is at the end we have this vertex un. Whatever is left on the stack, we draw diagonals from un to those vertices that are left on the stack at the end. And these diagonals are going to be safe to draw. And some of these vertices are going to be defining the edges of the polygon, so we may not need to draw vertex to the last one on the stack. For example, the last one on the stack is going to have an edge to this one. Also, this one also has an edge. So let's see. This is how our vertex looks like. Our triangle our polygon looks like before we come to the last vertex. So we draw all diagonals to, so if this is un, we draw diagonals to all the vertices except the top of the stack and the bottom of the stack. And this is going to finalize our triangulation on the Y monotone polygon. And this is a simple, by using a simple stack of data structure, we'll be able to triangulate this Y monotone polygon in linear time. Okay, so I mean, if we didn't have this algorithm, we could have an ON square algorithm as well to try to draw the diagonals between all pairs of vertices and see whether they're inside or outside, and see. I mean, but we could have this ON square algorithm in the first place in the simple polygon as well. I mean, in the simple polygon, you could have this in ON square time. You could try all the possible diagonals and whether they intersect the polygon or not. You could find that. Actually, after drawing a diagonal, you need to also check whether it intersects. So it's actually an ON cube algorithm. It's not ON square. So the naive algorithm is ON cube. Here we have in total, we have an n log n algorithm to triangulate a simple polygon. And we didn't actually do anything in both of algorithms. The existence of holes in the polygon, which makes it a non-simple polygon, actually we didn't do anything. We didn't assume anything about the existence of holes. Actually, these algorithms are going to be readily modifiable. I mean, even if your simple polygon has holes in it, you'll be able to decompose it into Y monotone polygons. Okay, the Y monotone algorithm that we discussed, the plane sweep algorithm, is able to also decompose any polygon, any simple, any not even non-simple polygons with holes into pieces that are Y monotone. So using these algorithms, you can triangulate any subdivision of the plane in ON log n time. But as I stated, we are not considering the quality of these triangulations yet. We don't consider whether we are going to have fat triangles or thin triangles. So this is an issue we are going to discuss later. Any questions about this? So this concludes our discussion about triangulating polygons. Any questions? Is it clear, the algorithm? Okay, so your homework from this chapter is going to be, again, about triangulation, but trying to triangulate a polygon for a different objective. Okay, so it is triangulating of a convex polygon. You'll be triangulating a convex polygon but then you say, oh, it's very simple, right? Pick any vertex and draw diagonals to any other vertices. But you are going to have a certain objective in this triangulation. We don't want, so we are going to, this is exercise 3.13 in the book. It's about it defines a number that is called stabbing number of a triangulated simple polygon, okay? It's the stabbing number is the maximum number of diagonals that are intersected by any line segment inside P, okay? So it's like this. For a convex polygon, so for a convex polygon, imagine you have a convex polygon like this. If you draw diagonals, so this is your convex polygon. Triangulating is really easy. Choose a vertex, draw diagonals to every other vertex. Now, the stabbing number is, if I draw a line segment within this polygon, how many diagonals it will intersect? Right now it intersects with 3 of them, right? I mean, in general, if you use this strategy to triangulate a convex polygon, but you can draw a line segment within this convex polygon, which is going to intersect ON diagonals, right? I mean, the order of diagonals that you are going to be intersecting is going to be ON. Here it's n minus 2. I mean, n minus 2 is ON, okay? So if you have an 100 gon, for example, with a polygon with 100 vertices, if you use this strategy, you are going, you can draw a line segment within this polygon which intersects all the diagonals you have drawn. Now, in this assignment, your goal is to come up with a triangulation, and you can devise an algorithm with any complexity. It doesn't have to be n log n complexity algorithm. Your goal is to have this stabbing number limited by log n. Okay, so find the triangulation of this convex polygon so that any line I draw within this convex polygon intersects at most log n diagonals. Okay, so it's a challenging problem. It's not very easy, but just think about it. How can you draw diagonals like this? I mean, as I said, the main hint here is that you can use very complex time, and you can devise algorithms which has high time complexity. So this eases your job a lot, actually. You don't need to devise an efficient algorithm, but if you can devise an efficient algorithm, that would be better. Not in terms of grades, but you'll be happier you found an efficient algorithm to do this. No, this is not even a diagonal, actually, because it doesn't pass through any vertex. So there is no rule. Any line that is drawn inside this polygon, any line, okay? There is no rule. You can draw any line, and you should guarantee that any line that you draw cuts these, intersect with at most log n diagonals. No, it's convex. So yes, it's a convex polygon. Okay, so this is going to be your next assignment. Now the question is, when are you going to turn this assignment? So I asked this question at the beginning of the first lecture. Are you guys planning to be here next week? I mean, if many of you have already planned vacations to go for a whole week, and if the class number is even less, we can consider, canceling next week's class. So maybe I can post something. I mean, if you don't want to answer right now, I can start a post in the news group about this, and let's see how many people will show up. I mean, if only 3 of you will show up, I mean, it means that most of the class is going to miss out the next lecture, so I don't want that. So we may cancel the next week's lecture. But
they're already being recorded. Maybe missing a class may not be that important. So even at least 3 or 4 of you show, but if nobody's going to show up, I'm not going to. I don't want to just talk to the camera. So I mean, if nobody is going to show up, then I may consider canceling the class. So I'm going to start a post in the news group about this in our news group, and please respond to that whether you are planning to attend next week's lecture or not. In any case. This homework is due in two weeks, okay, for those of you who are not planning to come next week. So you are going to have 2 weeks to work on this assignment, 3.13. I'm going to post it on the website also today. Any questions before we start chapter 4? All right, now we are going to talk about a new, challenging, different problem. It's a nice problem. It has a really practical applications. Now, first part is going to be understanding the geometry of the problem, and we are going to see the second part, solving this problem, is going to be just solving a linear program. And we are going to, after we formulate it, it's no longer going to look like a geometric problem. All right. So this, the title of this chapter is Manufacturing with Molds. So manufacturing with molds, then usually if the mold is used to manufacture a metal object, it's called casting. So the idea is this: you want to mass produce a certain object. Okay, imagine you're a company and you have a factory that you are going to go mass production. So for example, look at these erasers. So you are going to mass produce these plastic part of these erasers. So what do? You usually have a mold for this. I mean, you have like an iron mold that has the opposite of, I mean, its inside has exactly this shape, and you melt this plastic, you pour it into this mold, and then when it cools off, when it becomes solid, you just pull it out of the mold, right? So the question is, can you make any object with any shape? Can you design a mold for it so that when it dries off in the mold, with one action you pull it out of the mold? For example, if you had a sphere, this would not be possible. A single mold, you cannot, I mean, if you have a just small hole in the mold and you dry the sphere, oops, there's no way to get the sphere out of the mold. Either you have to break the mold so that the sphere inside is now in the open, otherwise, or you may have two different molds, half spheres, both of them half spheres. Then you break them apart in two parts maybe. Okay, so we are going to be talking about this today. Whether given an object, a design object, whether it is possible, we are going to ask this question. Is it possible to design a mold for this so that you'll be able to pull it from the mold without breaking the mold? Okay, so, and let's think about this problem first. We are going to have certain assumptions. First of all, we are going to assume that our objects are polyhedra, meaning that they are composed of polygonal faces, which are called facets, or I'm just going to simply call them faces, okay? A face of a polyhedron. And they don't need to be convex polyhedron. They can be concave, like we can have something like this. Okay, so this is
concave polyhedron. I mean, I just looking at one 2D projection. You are saying the 2D projection of this, but just consider this as a three-dimensional object. It's a closed object composed with faces that are composed of polygons. So the polygons can be triangles, anything. We don't have any restriction on the vertices of the polygons. But now the question is, can you design a mold for this? For example, a mold for this would be to have something like this. So we are going to assume that our molds are rectangular prisms like this. And so we can design a mold like this. So this may be our mold. If you pour melted iron or metal onto this thing, if it's and if it cools off, we'll be able to pull our object in this direction, and it's going to come out of the mold. But if your engineers don't know computational geometry that well, oh, well, let's have a mold for this, and I'm going to have the mold like this. Okay, this is our mold. Let's go mass production, and you will not be able to do it. In your first object, you are going to see that it's impossible to pull this out of the mold. Okay, so as you can see, this is the same object. Even the same object, sometimes based on which top face you choose to put on the top of the mold, it can be castable or it can be pulled out of the mold or not. So now we are going to decide, given such a polyhedron, we need to decide which face also to put at the top of the mold. And we can assume the top of the mold is always going to be horizontal, and it's going to be in parallel to one face of this one. So it has to be only one face has to be at the top of this mold. And if there are two faces, we cannot have a dry off the edges. I mean, if you cannot have two faces. For example, if imagine you want to have a polyhedron like this, okay? But if your mold is like this, there's no way to get this vertex there without a mold. I mean, it's not going to dry like this. It's just melted iron is going to be something like this. So in order to have, I mean, that's the reason of having mold. To define each face, we need to have all faces except the one face at the top inside the mold. And the one face at the top can be considered as the face that is horizontal, that is in parallel to the top of this mold, which has an open region that you can pull the mold out. Okay, so did everybody understand the problem? Okay, so there's a picture in the book as well. If you, I mean, I didn't draw it in 3 dimensions, so the 3-dimensional picture in the book describes this more clearly. So we are going to name this face of the object as the top face, and also this is going to be the top face of the mold. And here, for each other face of our object, there is a corresponding face in the mold. Okay? So each face of this object is defined by a face inside the mold. Okay? Let's call it the mold face. And what happens is that now let's consider the problem. How can we distinguish? I mean, why can't we pull this one out and the other one we can pull it out? So this is let's try to find out whether given an object and given a mold, can you find out whether it is if you pull it, you'll be able to take it out. And let me draw you another type of mold. Okay, in this one, let me get rid of. So in this one, so these are all So we can, maybe if you try to pull it this direction, it will not come out. But if you pull it this direction, it will come out, right? So that's another thing. So you don't necessarily need to pull it in plus, let's name it, this is Z, and this is X, Y, okay? So this is a different coordinate system. Let's have the Z coordinate at the top now. So here it doesn't necessarily be 0, 0, Z. 0, 0, I mean, it doesn't necessarily have to be your pulling direction does not necessarily be 0, 0, 1 direction. It may be, for example, 1, 1, 1 direction. But one thing is for certain, it has to have a positive Z component, okay? If you want to pull this thing out of the mold, I mean, either this one or this one, it has to have some kind of an up component. I mean, by pushing it, you cannot try to get it out of the mold in that direction. So it has to maybe have a positive Z component. Now, in addition to finding whether it is possible to take this out of the mold or not, we need to also find a direction. At which direction, if you pull, in which direction you should pull this so that it's possible to pull this, take this out of the mold. Okay. So we need to also find this direction. Now, here is the thing that we are going to observe next. In order for and let me ask you another thing. If I give you a polyhedra, do you need to make multiple moves? I mean, is a single move enough to take any object? I mean, or are there any objects in which, for example, you first pull this direction, then this direction, then this direction, it comes out. In a series of different directions, is it possible to take this out? And the answer is no. I mean, if a single move in a single direction, if it can be taken out from the mold, a single direction, a single translation is going to be enough to take it out of the mold. But there may be some objects which is not, I mean, we are not going to be considered, for example, a rotation of the mold. For example, if it's a screw is going to, you rotate the screw to take it out of the mold, but we are not going to consider rotation. This question is different from what I asked. I mean, I was asking whether it was possible to a series of translations, and rotation, we do not consider rotations in this regard. And a series of translations is no better than a single translation. This is what I'm trying to say. If an object can be taken out from the mold, a single translation is as good as a series of translations. So if it can be taken out, it can be taken out with just one translation in positive Z direction. Now, how are we going to solve this problem? So whether can we find whether a given direction. So if I give you something like this, if I give you a pulling direction x, y, z, and I know that let's say z is positive, x, y is not positive. So I give you a pulling direction, a pulling vector. How can you find out whether this pulling direction is going to take this object out of the mold? So we need to now look at the geometry of the problem. Here, let's look at these two different cases. And let's look at this direction, and let's look at this direction. This one cannot be taken out, but this one can. So in order to solve this problem, what other information we need? We need to, I mean, the shape of course is, we need the shape. The shape is really important, but what do we get out of the shape? What information we get out of the shape that we see this is not possible to remove, but this is possible to remove? Yes?
Mm-hmm,
If this is wider, it cannot be taken out.
Very good. So that's a very good observation. If but what happens? But you don't guarantee the sweep line may intersect the object in two different places. Imagine an object like this. It's consisting of two different parts and something like this. Okay? So if we have something like this, I mean, you need to also consider cases where your sweep line intersects with two places of this polyhedra. How are you going to define the width of this? The maximum of those, maybe? Consider them separately, maybe, yeah. But your friend's suggestion is this. If we have something during sweep line, we maintain, what we do is we maintain the width of the polyhedra that currently intersect the sweep line. So this width should be always decreasing. If any time we see that the current width is increased somehow, it means that we cannot remove this object from the mold. Okay, so is this a true statement? What do you say? I mean, it seems like a true statement to me. Can we prove this, or can we give a counterexample to this? I mean, I couldn't immediately give a counterexample, but I could say that, so the definition to define this, it may not be possible to define a single width. We may have objects like these. So our objects are not necessarily convex, so they can be concave. So, I mean, they can also, it means that they can also intersect the sweep line in two different places. So we need to consider cases as well.
If there's an increase in width, we cannot take it out, but if there is not an increase, we still may not be able to take it out if it's like this with decreasing.
Yes, that's a very good example. So it doesn't, we can see that, yeah, so this is a very good example. It's, yeah, so it's, yeah.
I have an idea of detecting that condition, but it must be combined with this one. My idea for that is we take each cross section in X and Y planes, not Z, vertical and like this, we slice the object. Those cross sections must consist of a single part. So if the polygon, if there's two parts in any cross section, we cannot take it out, because when we try to pull it, the bottom part will
always, okay. So that's a good idea. But practically then, when you have the cross sections, how many cross sections do you need? Infinite. So practically that means, but so did you understand the first part? I mean, it's the vice. I mean, let's go back to the first question. Even if we don't, so if we have an increasing width, it means that we cannot extract it from the mold. But it doesn't mean that if you always have a decreasing width, you still may not be able to take it from the mold. I mean, if the other condition does not work, I mean, it doesn't mean that it doesn't give you the fact that if it is a decrease, it doesn't give you conditions in which you are able to pull out. I mean, by looking at this width property, you cannot say I'm able to pull out this object from the mold because of because there may be cases in which even the width is decreasing, but you're still not able to pull out. For example, if it is something like this, the width is always decreasing, still decreasing here, still decreasing here, but you are not able to pull out this object from the mold. Okay, so if we have an object like this, we are not we cannot take this out of the mold because of the zigzagness of this. Of this face. I mean, this face is going to prevent us to get this whole object out of the mold. Yeah, it's, yeah. So yeah. There may be. But you can think about the solution in 2 dimensions as well. So 2-dimension solutions can be extended to 3 dimensions easily. Now, let me tell you the solution. Okay, so it's actually apparent from here. So any face, any mold face, in order to have a direction valid, if I'm able to pull this object with a given direction, this direction has to make a certain angle with all the mold faces. I mean, that angle cannot be, if we consider the normal vectors of these mold faces inside to the inside of the mold. This angle should always be greater than 180 degrees. If any time this angle is less than 180, it means that that face is blocking this direction. So, for example, this one, when we are defining the angle, we should also, for example, this one is not blocking because the angle between, actually not 180, 90 degrees. So we are going to consider this. So let me be correct in this case. Yeah, but how do we define that angle? So we need to define an angle of 2 vectors. So we have the normal vector and we have the direction vector. And these 2 vectors are vectors in 3-dimensional space. So what is the angle between these 2 vectors in 3-dimensional space? We define this as follows. We put both vectors on the plane. I mean, these 2 vectors can be put on a plane. And we assume both vectors are, we can pull both vectors to origin, their starting points. And the angle of the vectors is the smaller of the 2 angles measured on this plane. So it's like this. If we have these 2 vectors, we put them on the plane, there are 2 angles, right? This one and this one. The smaller of this angle is defined as the angle between these 2 vectors. So the angle between these 2 vectors is this. Now, here's the property. So the angle between this and this is less than 90. So this edge actually also blocks this direction. Actually, so just think about this. Look at this edge. This edge, if you try to pull towards this edge, actually at least you need to make an angle 90 degrees to slide that face. That if it makes 90 degrees, if your direction makes 90 degrees with the normal, your face is going to slide across that face. If it is greater than 90 degrees, you can directly take it out of that mold face. But if it is less than 90 degrees, or if it is equal to 0 degrees, it means that you are directly, this mold face is preventing this direction. But in that direction, you cannot pull your object. This face is going to block the object in that direction. Okay, is this clear? So here's in summary, a direction is a valid pulling out direction if it makes an angle greater than or equal to 90 degrees of the normals, inner normals of these faces. And it has to make this angle with all the mold faces. So that's another property. If there's any face, if it makes greater than 90 with n-1 of them, and there's one face which has this makes angle less than 90 degrees, that face is going to block the object. So the property is that a direction is a valid direction, is a valid pulling out direction if it makes an angle greater than or equal to 90 degrees with all the mold face normals. Now, the question is, yes? Yes, very good. So that's going to be our next natural step. So you cannot try
all the possible directions, which is our solution space is infinite. We know that it has a positive z component, but all the xy's, there are infinitely many different xy's, there are infinitely many different directions you can pull out in this space. So our solution space can be considered as if we take z is equal to 1 with no loss of generality, okay? We are going to be looking at this z is equal to 1 plane, so this is z is equal to 1 plane. So any point on this plane is going to define us direction. I mean z is equal to 1, this is z is equal, this is 0, 0, 0, okay? This is underneath this plane. Let me maybe draw it something like this. So this is our z is equal to 1 plane. This is 0, 0, 0. So any point on this z is equal to 1 plane is going to be a direction. Okay? Is going to define a direction or a pulling direction here. But as you can see, there are infinitely many such points on this plane. The next step is how do you, now the question is there a direction D with a certain xy which makes an angle greater than or equal to 90 degrees with all the mold faces? So yes, so yeah, this you're requesting a timeout. Yeah, it's time for break now. So after the break, we are going to continue with a solution to this problem.